Okay. Hello, everyone. I think we can start now. We're almost 3 minutes past the hour. Welcome and Happy New Year. Welcome to the first seminar of 2022 and the third seminar of this series on space propulsion, given by Professor Koizumi from the University of Tokyo and head of the Space Propulsion Lab. In case you haven't seen, this is the first time you joined this series of seminars and you haven't seen the other two, they were recorded and they're posted on our YouTube channel. So if you're interested, you can go there and check them out. As always, I don't think I have to say this anymore, but please keep your mics on mute and your camera switched off. And there will be a chance for you to ask your questions at the end of the seminar. You can either post them in the chat and I'll read them out loud, or you can just raise your virtual hand at the end and you will have a chance to ask them live. And with that, Professor Koizumi, you can take it away. Thank you.
Okay, thank you for the introduction. Do you hear me? Okay, thank you. And yes. So I'll sharing my presentation, right? Okay, so do you see my presentation? So this is PowerPoint and now slideshow. Okay. Okay, so I'll start. Thank you for coming. So this time I have to hold this seminar by a completely remote setting. Then I a little bit sad, but I'm very happy. A lot of people are coming here online. Okay, so let's start. Third class of this seminar is electric propulsion. Okay, so first I'll show you the this is third time and the main content of today. So first I will start from the fundamentals of EP, and after that categorization and also a little bit about plasma. What is plasma? And after the third and fourth chapters, I will pick up ion thrusters and Hall effect thruster. These two thrusters are, I say that they are major electric propulsion these days. So I'm focusing on these two thrusters. And also finally, I'll show you some application examples that are using electric propulsion systems. Okay, so first fundamentals. Let's start with a short review of the previous sessions. So as a first class, I talked about the energy source for propulsion system. So any kind of propulsion system is an energy converter from a certain type of energy to the kinetic energy. So in that sense, many types of propulsion system is possible. However, in actual usage, these days, only two types of energy sources are used. They are chemical reaction, so chemical energy type, and solar power, electrical energy type. So in the last previous class, I talked about the chemical propulsion, chemical energy source, and today I want to talk about this electrical energy source. In other words, solar power electrical generation. And also, as a first class, I talked about the difference of chemical propulsion and electric propulsion from the viewpoint of energy source. In the case of chemical propulsion, we can use the energy from the propellant. So we have oxidizer and fuel. These are propellant and also their energy source. So we have already energy. Then in terms of time, we can freely use those energies. However, when we try to increase the energy, we have to increase the mass also. So in this sense, chemical propulsion has very high flexibility for impulse by time. So impulse is the output of propulsion system, thrust times thrusting time. So this is output of the propulsion system. And time, thrusting time, you can arbitrarily determine this time. So flexibility for this time. On the other hand, there is a limitation for impulse by mass. So you have propellant and you have energy, but those are linked by mass. So mass determines the energy and the propellant mass. So impulse has a limitation, impulse by mass, and it is almost equal to exhaust velocity, and it's limited. And on the other hand, in the case of electric propulsion, you can freely choose the energy to mass ratio because you can get energy from the solar power. So if you wait and if you use long time, you can get more energy. So in that sense, impulse by mass, you can freely decide this value. So in this case, EP has flexibility for this value, impulse by mass. On the other hand, as I said, to get more energy, you have to wait more. You need more time. In that sense, impulse by time, this term has limitation. So this is the main difference between CP and EP. And in another word, this can be said like this. In the case of chemical propulsion, it has a flexibility for thrust, F. However, it has a limitation for exhaust velocity or specific impulse. And on the other hand, in the case of EP, it has a limitation for thrust. However, you can really determine the select exhaust velocity. So here, this time, today, let's see this in more detail by using some numbers. So again, this slide shows the energy conservation. Wait. Energy conversion of energy conversion equation. So you have a certain kind of energy. This here, energy, and to convert it to the kinetic energy, you will have some kind of efficiency, conversion efficiency. And the second term is kinetic energy, and here you see the propellant mass. And also third term, I deformed the equation by using this thrust equation. So thrust can be expressed by using m dot times UE. M dot is the mass flow rate, and UE is the effective exhaust velocity. So by using this equation, third term, we can get third term. And here you see thrust and thrusting time, and also exhaust velocity. So this is a very basic relation between energy and kinetic energy, or energy to the thrust. So what happens in the case of chemical propulsion? Yes, in the case of chemical propulsion, energy should be proportional to the mass because fuel and oxidizer, they are energy source. So you have here certain kind of coefficient, and energy and mass are related by this equation. And by using this equation, you will get these relations. So you will immediately understand that UE, exhaust velocity, should become like a constant, like this. So it's determined by this coefficient alpha and energy conversion efficiency eta. On the other hand, thrust, the thrust has this kind of form. And here you see that thrust is related to this term, m by t. In other words, thrust can be adjustable by this m and t term. And m and t is like a m dot, mass flow rate. So by increasing the mass flow rate, you can increasing the thrust. So this is adjustable term. Okay, so this relation is changing in the case of EP, and let's see this relation. So in the case of electric propulsion, main difference is here. Energy is proportional to the time. So we are using the solar power generation, and if we use more time, we can get more energy. So by using this equation, you will get these kind of two relations. It's a little bit different from the chemical propulsion case. And here you have a constant like terms to eta beta. So this is almost same as a chemical propulsion case to eta alpha. So this is almost a constant term. And here you see these two important terms. So again, m by t or t by m appear here. And you see these has reciprocal relation. So if you increase the UE exhaust velocity, this thrust must be decreased. And if you increase the thrust, UE must be decreased. So there's a reciprocal relation between that. But they are both adjustable. So there's no basically limitation. By adjusting these terms, you can select the ratio between U and F. So this is the main feature of electric propulsion. And basically, when you use electric propulsion, basic motivation is you want to increase the exhaust velocity. And this means you have to decrease the thrust F term. And also, let's see the actual numbers of these relations. So they are very typical numbers that are used for electric propulsion devices. So first, here I use energy conversion efficiency, 50%. So well-designed thruster has this kind of value. And for beta, so this means power generation, solar power generation. Let's regard 400 watt. So this corresponds to the 1 squared meters and energy conversion of 30%. And 1 AU from the sun. This is a distance. So this is very important for the power generation. And the mass is 10 kilogram. So this is just for reference. So 100 kilogram or 1 kilogram you can freely use. But here, as an example, let's set it as 10 kilogram. And also time is also reference, but here, let's pick up 1 year. It corresponds to the 30 megaseconds. So by using these values, for example, you can get these numbers. As to UE, exhaust velocity, 36 kilometers per second. And as to force thrust, you get 11 millinewton. So you can get very nice exhaust velocity, 10 times higher exhaust velocity than chemical propulsion. However, the thrust is much less than chemical propulsion's case. In the case of chemical propulsion, thrust level is at least 1 Newton and easily 1 kilonewton and sometimes 1 meganewton. So this millinewton is quite a small value. And it is due to the power limitation that we can use in space. Okay, so this is a very basic of the fundamentals of EP. So EP is a very good propulsion device, and you can increase the exhaust velocity up to very high value. However, for that, you have to decrease the thrust. So basically, how to use the electric propulsion is very different from the chemical propulsion. Okay, so second chapter is a categorization and plasma. So actually, in electric propulsion, there are a lot of types of thrusters. So here I will show that categorization. So first, I will show you 3 acceleration processes that is used in electric propulsion. So by using this acceleration process, we can categorize electric propulsion thrusters. So first method is electrothermal acceleration. In this case, first, it's starting from the electrical energy, and this energy is once converted to the thermal energy by using Joule heating. And this thermal energy is converted to kinetic energy. And here we will use nozzle. So this process, thermal energy to kinetic energy, is completely same as a chemical propulsion. So only the difference is a heating method. So how to get thermal energy. And here we use a Joule heating. And the second acceleration is much different, electrostatic acceleration. So here, by using electrical energy, we are directly converting this energy to kinetic energy by using electrostatic force, as Coulomb force. So in this case, direct conversion from electrical energy and kinetic energy. So energy conversion efficiency is generally higher than the electrothermal case. And the final example is similar with electrostatic acceleration. This is electromagnetic acceleration. So in this case, electrical energy is also directly converted to kinetic energy, and it's by electromagnetic force, in other words, Lorentz force. So these are main three acceleration mechanisms in electric propulsion. But here you see that any acceleration process uses electromagnetism, Joule heating, electrostatic force, and electromagnetic force. Yeah, it's of course, because we want to convert electrical energy to the kinetic energy. However, if you use a normal material, like gas or any kind of solid, liquid, usually those materials are neutral, and they show no reaction against electromagnetic force or electrostatic force or Joule heating. No conductive insulator and no electrostatic force and electromagnetic force. So to use these acceleration mechanisms, basically we need plasma. So plasma is one type of state of the material, like a solid, liquid, gas. So sometimes we regard plasma as a fourth state of the material. So solid, liquid, gas, plasma. And in space, there are a lot of plasmas actually. So actually the sun is a huge bunch of plasma, and also lightning is also plasma, and aurora, a lot of things. So this plasma has property to respond with electromagnetism. So we will use plasma for electric propulsion. And this slide shows what is plasma. So in macro scale, I can say it as an electrical gas. So it's just a gas with electrical property. And in micro scale, I will explain it as mixture of ions and electrons and neutrons. So, and here I said ions and electrons. And when you hear ion, you might imagine the ions inside the liquid. So inside this kind of liquid, you have sometimes you have negative ions and positive ions. But here, this ion is different from this kind of liquid ions. So this is inside, how to say, like a gas state. So each particles are not strongly related to the next to the particle. So it's like a gas state. And this electron is coming from the neutral particles. So if you have a neutral particles, and when you remove one electron to outside, you will get ion and electron. So plasma is a mixture gas of these ions and electrons, and also remaining neutrons. And here, I'm briefly explaining the basic features of plasma. So plasma is a very complicated state, and so there is a plasma physics, but inside that there are a lot of phenomena. So I cannot explain all of those things, but here I will show you some typical features of plasma. So I picked up three features of plasma. So first one is the interaction with EV field and rarefied gas and a mixture of completely different nature. So first one, interaction. So as I said, it's like a gas. So in that sense, basic equation is almost same as fluid dynamics. So sometimes we use this kind of, it's almost same as a Navier-Stokes equation, fluid dynamics equation. But the different point is we have three types of particles, ions and electrons, neutrons. So basically, we need 3 equations. Although in this slide, I have written only 2 equations, but basically we have 3 equations. So we have to solve these 3 equations instead of only 1 equation. And also another difference is here. Of course, ions and electrons are responding to the electric field and the magnetic field. So we need to include these terms into the fluid equation. And also, other important point is ions and electrons have charges, positive charge and negative charge. And if those particles are moving, current are generated here. So depending on the density and the velocity, currents are generated. And these currents lead to magnetic field and electric field. And again, these B and E fields affect this fluid dynamics. So this is the interaction. So you see, plasma would be very complicated because it includes fluid equation, 3 times fluid equations, and also Maxwell equations. And the second point is continuum modeling is not valid. Although I showed this fluid equation, but unfortunately, in usual cases, we cannot use that equations. So when we use fluid equations at each point of space, particles' behavior can be represented by using macro quantity like density or velocity or temperature. So this is a kind of approximation, but this approximation is valid only when you have huge amount of particles at a certain point, and if you have enough collisions at that point. And usually fluid, gas around us satisfy this condition. However, in the case of plasma, usually gas density is not so high, and collision rate is much lower than the standard gas. As a result, in most of cases, we cannot use this continuum modeling, continuum assumption, and we cannot use fluid equation. So instead of those, we have to use Boltzmann equation or direct simulation of particles. So Boltzmann equation is also differential equations, but it includes velocity space. So actually 6D simulation is required. And in the case of direct simulation, you have to simulate all of the particles. And you know that inside a certain space, unbelievable number of particles are included and very difficult to solve. And the final feature is a completely different nature. So we have ions, electrons, and neutrons, but they are so different. So in the point of charge, yeah, of course, neutrons has no charge, but ions has positive and negative, electrons has negative. In the point of mass, neutron and ions are almost same mass. However, electrons is ultra lighter than those materials. And due to this mass, typical velocity of electrons and ions are different. Usually, ions has in electric propulsion systems, it has a velocity of 3 kilometers per second or something like that. But electrons has a almost 2 megameters per second velocity, so very high. And instead, neutral particle is slower than those. And also, due to these mass and velocity features, gyration around the magnetic field, gyration radius is also very different. So no gyration for neutral particle, but the ions has, for example, 2 centimeter radius, but electrons has much smaller radius. So anyway, these particles behaves in completely different manner. So it leads to very high complexity. Okay, so let's return to the categorization of electric propulsion. So most of the propulsion systems are using the plasma, and so they have to first generate plasma, and after that they accelerate those plasma to outside. And as I said, for that acceleration, there are three types: electrothermal, and electrostatic, and electromagnetic. And they are typical thruster types: radiated thruster, Arcgis Thruster, gridded ion for effect thruster, field emission, Electrospray, MPD, plasma thruster, and magnetic node thruster, many. So from now, one by one, let's see. So first one, radiated thruster. So this thruster is the simplest thruster in my electric propulsion thrusters, I think. So actually, this thruster does not use plasma. It uses just resistor heating. So here you are using resistor, and by using this resistor, Joule heating, you can warm up the gas temperature. And this high temperature gas is ejected through the nozzle. So only the difference from the chemical propulsion is a combustion or Joule heating. So in this case, then this thruster is very simple. So applications are many, and what includes a gas, hot gas. But its thruster performance is very similar with chemical propulsion, as you can expect. So exhaust velocity is almost the same as a chemical propulsion range, 1 to 5 kilometers per second. And power range is, it's depending on the power source you use, but from 10 watts to 2 kilowatts, many range. And the second example is Arcgis Thruster. This is using a plasma. So here you have a plasma, and through this plasma, there is a discharge. And this discharge warm up the gas temperature. So it increases the gas temperature. So we can get higher temperature than radiated thruster. But this is again electrothermal acceleration type. And this Arcgis thrusters also has many application examples, and work includes the plasma. And the exhaust velocity is a little bit higher than radiated thruster. And to generate discharge, power range is usually around 1 kilowatt, so not too small. And the next example is gridded ion thruster, or simply ion thruster. This is one of the most major electric propulsion systems. And I will explain the detail of this thruster later. But simply, this is electrostatic acceleration. So first, it generates plasma here, and only ions are electrostatically accelerated to the downstream. So this is gridded ion thrust. And the next one is also another major electric propulsion thruster, Hall effect thruster. So this thruster also accelerates ion by electrostatic force, but appearance and inside is so different from the gridded ion thruster. And very unique appearance is this donut-like plasma, so annular shaped plasma. And inside that, ions are accelerated to outside. I will also explain this thruster in detail later. Okay, next example is a field emission electric propulsion. So recently, actually, in this 2 or 3 years, many these thrusters are flying in space, start to fly in space. And this field emission means we extract ions from the metal liquid. So in this case, first, we don't generate plasma. We directly extract ions from the liquid state by using very high electrostatic field. So for that, usually acceleration voltage is very high, like 10 kilovolt. And as a result, exhaust velocity becomes very high value, 50 kilometers per second or something like that. Of course, high exhaust velocity is very nice. However, as I said first, this exhaust velocity is related to the force, and high exhaust velocity means low thrust. So due to this very high exhaust velocity, typically this field emission electric propulsion has low thrust, typically less than 1 millimeter, 0 point something. And the next one is the Electrospray thruster. This is almost same as a field emission electric propulsion, but instead of a metal liquid, typically it uses ionic liquid. And due to this propellant difference, typically exhaust velocity is lower than the FEEP case, field emission case. So ionic liquid has larger molecular weight than metal liquid. So exhaust velocity becomes lower. And also in this thruster, sometimes ions are directly extracted from the ionic liquid, or sometimes liquid droplets are generated. And that liquid droplet has a charge, positive or negative charge, and they are accelerated to outside. And common point of this electrospray thruster and field emission thruster is we need very thin, small electrode tip here or here to generate very strong electric field. Due to that, usually the size of thruster is very small. So typically, one emitter has a scale of 1 millimeter or something like that. So very small. And to increase the thrust, we need to increase the number of these tips electrodes. So 10 electrodes, 100 electrodes, or 1,000 electrodes to increase thrust. Okay, next thruster is a magnetoplasma dynamic thruster. Sometimes it's called as a MPD. And this thruster uses electromagnetic acceleration, so third category. And this MPD is considered as suitable for very high power usage, like 100 kilowatt. But so far, only a pulse demonstration was conducted in space. So I say that MPD thruster is still in research phase on the ground. So electromagnetic, here we are using electromagnetic force, but inside that, the physics is very complicated and it's very difficult to optimize the thruster shape or operating method. So still now it's under research phase. And also this is another one, but in electromagnetic acceleration called as pulse plasma thruster. So this also uses electromagnetic acceleration, but it uses a pulse to discharge. And sometimes we use solid propellant here, but this solid does not mean explosive. This solid is typically polymer, typically PTFE, in other words, Teflon is used. And this PTFE is ablated by the discharge, and this ablated gas generates plasma. And inside that plasma, electromagnetic force accelerate is applied, and the plasma is accelerated downstream. And typically, this plasma thruster is designed for small thruster, miniaturized thruster. So like this, the size is this size, and the typical power is a 10-watt range. So by using pulse discharge, we can generate it very high current by using not so much energy. So by using this kind of power level, we can generate electromagnetic acceleration. And also in many cases, simultaneously electrothermal accelerations are occurring. Okay, so final, this is an example, magnetic nozzle thruster. So this is again very huge thruster, its concept. So in this case, we are using the electromagnetic acceleration, but it's a little bit different from the MPD. So basically, it generates plasma by using electrode-less plasma generator by using high frequency, like radio frequency. And sometimes those plasma type is a helicon plasma or ICP, inductively coupled plasmas. But anyway, electrode-less plasmas are utilized. And generated plasma is accelerated by using magnetic nozzle. So here you see nozzle-like structure, but it's just a shape and material. And actual nozzle is not this solid material. Inside here, there is a magnetic field line. And along to these magnetic field lines, plasma are exhausted to outside. So this is magnetic nozzle thruster. And this thruster, its operating point is also very high power point. And not yet, this thruster is not applied in space. Some startup companies try to use this thruster and its miniature version, try to use in space, but not yet application phase. Okay, so as you see, there are many types of electric propulsion thrusters, and features are very different from thruster to thruster. But here I wanna pick up two major thrusters, as I said, gridded ion thruster and Ford effect thruster. So first, let's start from gridded ion thruster. So this is the same slide that I showed. It's a gridded ion thruster. And so this slide shows a detailed mechanism of plasma. So first, you have to generate plasma. And for that, we have certain kind of chamber. It's called as a discharge chamber. And here we input gas and electrical power. Here I wrote microwave power, but RF power or DC discharge, any kind of electric power is okay. And when we input power and gas into the chamber, after some plasma generating process, we create plasma here. As to this plasma generation, later I will explain. And after you generate plasma here, by using electrodes called as grid, these electrodes. By using these electrodes, only ions in this slide, blue particles, are extracted and accelerated. And they are going like this. And also, you need to also emit electrons. Otherwise, electrons remain inside the satellite, and these negative charges will decrease the potential of the satellite. And this decreased potential will attract ions that are ejected to the outside. So eventually, ions might come back to the satellite. And it means thruster does not work. So to neutralize the satellite potential, to keep the satellite potential, we have to emit same amount of neutral electron particle to outside. And that function is conducted by neutralizer. So it can be called as an electron emitter. So these three processes are basic process of ion thruster: plasma generation, ion acceleration, and electron emission or neutralization. So first, let's see the example of electrostatic acceleration. by using grid. So typically, grid system has this kind of configuration. So you see these small apertures, typically 1 millimeter or 2 millimeter or something like that. And you have 2 or 3 grid systems. So in this slide, left-hand side is inside of the discharge chamber, and the right-hand side is outside of the chamber. And through these apertures, ions are accelerated. So here you see the example of calculation of ion trajectory. Here, yellow curves shows ion trajectory, and red curves are electric potential. So by using these 2 grids and the 2 apertures, we can extract ions from inside and accelerate like this. And as plasma generation, these days, there are 3 types of plasma generation that are used for ion thrusters. And the most major discharge method, plasma generation method, is called as a DC discharge. So this is inside the plasma generator, discharge chamber. And you have electron emitter. So this is different from the electron emitter that is neutralizing the plume, that is keeping the satellite potential. This electron emitter is to generate plasma inside plasma generation chamber. So this electron emitter emits electrons, and here you have a DC power source and the electrode here. So current flow like this is produced, and this current flow and electron flow ionize the neutral particles and generate a couple of ion and electron. So this discharge generates plasma. So this is called as DC discharge type. And one typical example of this type of thruster is T5. This is developed by Kinetic, a UK company, and this size of thruster. And the next example is RF discharge plasma generation method. So ICP is an inductively coupled plasma, and one of the plasma generation method by using high frequency, radio frequency. So here you see coils, and by applying high frequency current to this coil, you can generate alternating magnetic field inside the discharge chamber, and this alternating magnetic field generates azimuthal electric field. And this electric field causes a discharge inside. So by using this mechanism, also we can generate plasma. And one typical example of this thruster is a RIT series that is developed in Germany. So you see here, so this is a mock-up model, but here you see coil-like curves, and this is a RF coil, and plasma is generated around this. And you see grid system. And the final plasma generation method is microwave discharge. So in this case, similar with RF, we are using microwave. And microwave is a microwave has typically a frequency of gigahertz, 4 gigahertz, or 10 gigahertz like that. And by using this microwave, we can produce plasma. Typically, by using electron cyclotron resonance, we can generate plasma. So, typical example of this technique is Hayabusa 1 or Hayabusa 2's ion thruster. So, this was developed in Japan. And this is a outside appearance, but inside there is a microwave antenna, and that microwave is propagating inside the discharge chamber and generate plasma. So As I explained, ion thruster has 3 steps: plasma generation and acceleration and electron emission. And basically, these 3 steps are separated. And this is a very nice point of ion thruster, I think. So the 3 stages are separated. We can focus on one of those steps when we developed a new thruster. So when you want to increase the plasma density, you will focus on the plasma generator. And if you want to increase the acceleration, you will focus on the electrode grid system. So this is a good point of ion thruster. But ion thruster has very big demerit. So from now, I want to explain about that. So this is a very simple model of ion thruster. There is a plasma and you want to extract ions to outside. And if you want to increase the thruster, this thrust. So if we want to increase the thrust, what you should do is to increase the number of ions flowing to outside, of course. But ions has positive charge, and a number of ions are repelling each other. So if you increase the number of ions flowing downstream, at a certain point, this ions repelling force is too strong, and this force prevent additional ions are going to out. So this phenomenon is called as a space charge limitation. So if you increase the ion flow through the grid system, there is a limitation. There is an upper maximum, upper limitation of the ion flow. And this means in gridded ion thruster, there is a limitation of the thrust per unit area. So if you want to increase the thrust more, what you have to do is you have to increase the area of the ion thruster or grid system. And what will happen is like this. You have to make huge grid system like this. This is an old days ground experiment model, but you see this size is so big. But simultaneously, you have to prepare very severe alignment between grid systems. So you need 2 or 3 electrodes to extract ions. And typically these grid systems are aligned in the scale of 1 millimeter. But if you make this kind of gigantic ion thruster grids, yeah, you can imagine that it would be very difficult to accurately align 2 or 3 grid systems. So this is a main demerit of a gridded ion thruster. So here, let's consider the countermeasure for this problem. How we can avoid this problem. Okay, so basic problem was ion charge, ion positive charge. So between grid system, only ions are flowing, and those ions are creating positive charge. So this was a source origin of problem. So to avoid this problem, very simple idea is let's put electrons between grid systems. Then electron has a negative charge, so space charge becomes neutral. That does not create any potential here, so positive potential. So you may flow a lot of number of ions to downstream. However, there is one problem. Of course, by electrostatic field, electrons are accelerated opposite direction. In this case, left-hand side. And additionally, electron has much smaller mass. And this means electrons, this motion, it's much, much quicker than ion motion. So immediately after you put electrons into this grid system, electron will be lost. This is a very big problem. We have to fix electrons. And for that, magnetic field can be used. By using magnetic field, charged particle can gyrate around the field lines. And if you adjust the strength of magnetic field properly, electrons gyration is like this. Gyration radius is like this. But ions gyration radius is like this. It can be achieved by adjusting the field strength because mass of ions and electrons are so different. We can realize this kind of setting. Then only ions can be accelerated to downstream, and ion gyration, its radius is very large, and ions are not trapped inside that. However, electron, its radius is very small, and only electron can be trapped inside this area. Yeah, it's a very nice idea. But there is another effect for electrons. If you have electric field like this and magnetic field like this, electrons start to move perpendicular to this right direction. So this way or this way by electric field. So this is called as E-cross-B drift, and the very basic nature of the electron motion inside E and B field. So this means these electrons can be lost along to the perpendicular direction to this screen. So if we wanna prevent this motion, this is E-cross-B drift. And what should do is like this. Okay, so let's make an azimuthal configuration like this. So this is not easy to draw on the PowerPoint, but yeah, I hope you understand this concept. So by using by slightly curving the this configuration and roll up one circle, you can E-cross-B drift becomes azimuthal direction. So E-cross-B drift is just this kind of rotation, and there is no electron loss. So this is a Fourier effect thruster. Historically, I think it's different, but in physics, for thruster is like this. So by putting electrons inside discharge channel, electrostatic acceleration region, we can neutralize the state, and we can avoid space charge limitation, and we can increase the thrust by using a small area. Okay, so this is chapter 4 for the thruster. Let's see more detail. So the feature is electrons simultaneously exist around here, and ions are accelerated to outside by using electrostatic force. And these electrons are azimuthally rotating by E-cross-B drift. Okay, so first let's see the thruster feature. So as I said, by using this configuration, well, by using Fourier effect thruster, we can increase the thrust density, thrust per area. So let's see that effect. For example, this is the two famous ion thrusters. One is a PPS 1350, and this has roughly 10 centimeter diameter, this diameter, and its thrust is 90 millinewton. And the right-hand side is a gridded ion thruster, Hayabusa 2 ion thruster. That diameter is the same as left one, 10 centimeter, but thrust is a 10 millinewton. So you see the difference of the thrust with the almost same area, diameter. So this is an effect of Fourier effect thruster. But in the point of energy conversion, both thruster has almost same efficiency. So here you see the difference of these values. So when you see the power, so power is so different. Right-hand side, left-hand side is a 1.5 kilowatt, but right-hand side ion thruster is just 0.35 kilowatt. So more than 4 times difference. And also here you see exhaust velocity. Here I show the specific impulse (ISP), but in terms of exhaust velocity, this is 15 kilometers per second exhaust velocity, and here is 30 kilometers per second exhaust velocity. So double difference. But the merit advantage of horrific thruster is by using a small area, you can realize high thrust. Another comparison is like this. If you realize the same amount of thrust by using grid ion thruster, you need this kind of area. So in this case example, N-star, this is also very famous ion thruster developed by NASA, and very nice, very high performance. And in this case, diameter is 30 centimeter. And thrust level is almost same. But area is almost 9 times. So you can understand the effect of horrific thrust. Please. And the next, I will explain inside of the horrific thruster more. So, but yeah, honestly, horrific thruster, its physics is very complicated, especially when you compare with ion thruster, grid ion thruster. So I'm not sure in this short time I can fully explain the physics, but yeah, let's try. Let's see. So as I said, E-cross-B drift is very important physics inside the horrific thruster. So if you have a E and B, electrons are drifting in direction to perpendicular to B and E both. So in this example, this direction. And also, if this electron collides with neutral particle, this drift line is slightly shifted towards a positive potential direction. In the case of a Hall thruster, upward, upstream region. So collision has a little effect to shift this drift motion. So as a result of these two effects, Hall thruster's operation can be explained like this. First, here outside, there is an electron emitter, and this electron emitter emits electrons. Most of the electrons are going to downstream. Most electrons are going to downstream to neutralize plume. But certain fraction of electrons are going to inside. Maybe 10% or 5% electrons are going to inside. And these electrons are trapped by magnetic field and started to E-cross-B drift in azimuthal direction. But when these electrons collide with neutral particles, they are slightly going to upward towards the anode. And when electrons goes to the upward, electrons can get energy from the potential. So upward is the highest potential part, anode. So when electron goes to the anode, electron get energy. So gradually electron getting energies. And eventually when electron hit neutral particles, sometimes ions are generated by ionization. So this is the plasma generation mechanism of horrific thruster. And the generated ions are accelerated to downward. And additionally, generated electrons are again going to the upstream. So this is a current flow summary of horrific thruster. As I said, here the electron emitter, and most of the electrons are going out but some electrons are going to inside. And these electrons, they are called the backstreaming electrons. They can get energies from the potential. Then they can ionize neutral particles, generate ions and electrons. And generated ions are going to downstream, and the generated electrons are going to upstream. And as an electrical circuit, there is one big electric current loop here, this direction. So close to anode area, current carrier is electron. And inside the channel, electron current carrier is ion and electron. And near electron emitter, current carrier is again electron. So there is a one current path loop, but inside physics is so complicated. But as I said, by using this mechanism, Hall effect thruster realized very high density thrust by using neutral plasma acceleration. Okay, so finally, let me show some application examples of these electric propulsion systems. So these days, there are many electrical propulsion applications, but I picked up only 4 examples. But if you check the web, you can find more applications of EP. So first one is Gaussian by ESA, launched in 2009. So unique point of this satellite is its appearance. So you see very cool appearance of the satellite. So this is for drag compensation. So this Gaussian was flying very low Earth orbit, 200 kilometer altitude or something like that. And there are a lot of atmospheric drag. So without propulsion system, shortly satellite will go down into the atmosphere. So satellite cannot fly a long time. So the purpose of electric propulsion in Gaussian is this atmosphere drag compensation. And also to reduce this drag effect as much as possible, they designed very cool satellite shape. So long towards flying directions, and there are solar panels, but those solar panels are designed not to produce additional drag. So it's great. So in one article, I have heard that they said this Gaussian is called as Ferrari in space. Although I have never heard such kind of people that they say this is a Ferrari in space satellite. But I think it's good naming. Actually, it's very smart, cool appearance. And so this is one of my favorite satellite. And mission purpose of this Gaussian is a very accurate measurement of Earth's gravity field. So by flying very low Earth altitude, it can accurately detect the gravity field difference rather than high altitude satellite. So actually 1/millionth of 1G measurement was conducted by using this Gaussian satellite. And the next example is a Japanese small asteroid explorer Hayabusa. And especially the satellite appearing on this slide is Hayabusa 1. So Hayabusa has 2 satellites, Hayabusa 1 and Hayabusa 2. And I was involved in Hayabusa 1 project. So I have a lot of impression for this Hayabusa 1 satellite. So I picked up this Hayabusa 1. So it has a weight of 500 kilogram and propellant is 60 kilogram. And the delta V generated by ion thruster, it was 2.2 kilometers per second. And the destination of this Hayabusa explorer is asteroid Itokawa. So Itokawa's rough orbit is like this. So its apogee is further than Mars orbit, and its perigee is inside Earth orbit. And the remarkable feature of this Hayabusa is its round trip to asteroid. So basically, deep space exploration is one-way travel. Going to the destination and the observation, that's all. No return. However, in this case, the purpose is a sample return. Then its journey was round trip. And for that, we need high delta V. And in this case, it was conducted by ion thruster. And in this case, we used a microwave discharge ion thruster. And microwave discharge, one of the features is simplicity. So, and in other words, robustness. So after the long journey, it can succeed to return to Earth. Actually, total operating time is 40,000 hours, so very long. At that moment, this was a world record. And the next example is Dawn by NASA JPL. This is also very great satellite. Especially remarkable point is the delta V, 11 kilometers per second. So huge delta V generated by ion thruster, ion propulsion system. The satellite size is almost double of the Hayabusa, and the propellant 400 kilograms, so much. And also you see a large solar array panel to drive ion thruster systems. So this solar array panel near the Earth, it generates 10 kilowatt, enough electric power. And this is an ion thruster that was used in Dawn N-star. And the 3 N-stars are used for this Dawn mission. And thrust is 90 millimeters, much higher than Hayabusa ion thruster. And next, I want to show the orbit of the Dawn spacecraft. And before that, I want to show you the spiral orbit raising. I showed this slide on the first class. And typically, electric propulsion uses this kind of orbit transfer. So by thrusting along to the tangential direction, its orbit is gradually increasing. Orbit altitude is gradually increasing like this. And this is actual orbit of spacecraft Dawn. So here Earth, so departure, and Dawn orbit is trajectory is like this. And on this line, you see two colors, blue and orange. And orange is a coast. This means just flying, so ballistic flight. And this pale blue color is thrusting time. So with ion thrust operation. So you see after the departure, Dawn started to use ion thruster, and on and off repeated. And when it close to approaching to the Mars here, it turned off the ion thruster at this point and approaching to the Mars. And here it conducted a gravity assist a little bit and going to like this way. Then after that, around here, it started to operate ion thruster. Then orbit radius is gradually increased like this. And here, it reached to the, this is a Vesta. Sorry. So this yellow line is a Vesta orbit, and this purple line is a Ceres orbit to asteroids. After observation of Vesta, it departed Vesta, left Vesta, and ion thruster again operated. And here you see gradually radius is increasing like like this. And here it arrived at Ceres and observation and end of mission like this. So it's a very nice example of orbit spiral raising, I think. This slide shows a asteroid Vesta and Ceres, and that were observed from the Earth by using a Hubble telescope. And from the Earth, this is a limitation of the resolution. So Vesta and Ceres are observed like this. And this is actual photographs taken by dawn. So going to the place asteroid has great effect. So by crossing to the asteroid, you can get this kind of resolution, so much difference. So I like this comparison. Okay, so final example is Bepi-Colombo. This is a Mercury orbiter launched in 2018, and still now it's flying towards Mercury. And the observation may start 2024, so 2 years later. So I wanna show you this spacecraft. So first feature is its color. So on this slide, you see very white spacecraft, very rare, strange, curious spacecraft. Usually spacecraft color is yellow or black, or those colors. However, this Bepi-Colombo has this kind of very white shape. I think it's very cool. And this is, of course, it has a very clear reason. That is, it is very close to the sun. So it's going to the Mercury, and the Mercury distance is 58 million kilometers from the sun. So it's almost 1/3 compared with Earth's position. And this means very high sunlight, and it means a very high sun heat flux. So to avoid that, to reflect sunlight as much as possible, it needed to install these white colors. And this Bepi-Colombo has two propulsion systems. One is electric propulsion and one is a chemical propulsion. And electric propulsion for orbit transfer, and its total delta V is almost 5 kilometers per second, very high value. And also, to become Mercury orbiter, it needs to generate high thrust within a limited time. And for that, we need chemical propulsion. So Bepi-Colombo has this chemical propulsion for orbit insertion. And additionally, this Bepi-Colombo uses gravity assist many times. So Mercury is very difficult observation target or destination target because its distance is very close to the Earth compared with Jupiter or Saturn. However, its potential difference between Earth and Mercury is so large. And going to Mercury is very difficult work. So this Bepi-Colombo uses all of the technique to change its trajectory, electric propulsion, chemical propulsion, and also gravity assist. So finally, let's see the trajectory of the Bepi-Colombo. Before that, this is an ion thruster that was used in Bepi-Colombo T6, very big ion thruster, 130 millinewton. This is the highest thrust ever that was used in space. Okay, let's look at 6-year journey. Okay, so this is trajectory. So compared with the dawn trajectory, you will understand immediately it's too complicated and very complicated. So, but yeah, it's very fun to understand this trajectory. So let's try. Okay, so first, this is first phase. So departure is 2018 and October 20th. So this is departure. So in this slide, oh wait, yellow orbit is a Earth orbit, and the gray orbit is a Venus orbit, and the red orbit is a Mercury orbit. Okay, please wait a little. Yes. So this is departure. And Web column is first going to like this. And this pale blue curve and the purple curves are Web column's trajectory. And here, this pale blue means ion thruster off. It's different from the drawn example, but yeah. And this purple color means ion thruster on. Okay. So first, no ion thruster operation up to here, and here it starts to operate ion thruster and going like this. At this point, Web column's orbit intersect with Earth's orbit, but here there is no Earth. I mean, Earth was at a different position, so Web column did not meet us at this point. So just going to Earth, and after one rotation and a half, one rotation and again half, it meets with Earth, and Web column conducted gravity assist here. Yes, this one. So almost 1 year and a half later, it conducted gravity assist by using Earth. So after this gravity assist, its trajectory is going to innerward from the Earth orbit. So going to like this. So yeah, like this. And 2020 October, Web column meet with Venus here, and it conducted a Venus gravity assist #1. And after this gravity assist, it's going to like this. And again here, it meet with Venus again and conducted gravity assist. This is 2021 August. And after this gravity assist, it's going to inside more. Maybe one more rotation it conducted, but yeah, it's very difficult to see from this figure. But yeah, I think yeah, 2 rotations and going to inward. And here, this is 2021 October, Mercury gravity assist #1. And after that, here it's almost impossible to trace the actual trajectory of Web column, but yeah, it conducted Mercury gravity assist #2, #3, #4, #4 and #5 and #6, and finally 2025. It becomes Mercury orbiter. So it's very long journey and very complicated trajectory. So very careful operations are required for this mission. Very challenging one. But I like these trajectories. And ESA, they have very nice website to check today's Web column's status. So if you are interested in, please visit this site, and then in this site you can know the current position or current history of the Web column by using intellectual interface. And yeah, finally, yeah, I'd like to mention about it. So this Web column is a Europe and Japan joint mission. And actually, it has 2 modules to observe Mercury. One is a European MPO, and another one is a Japanese MMO. And MMO was this. And this MMO was developed in Japan, and yeah, a few more than 5 years ago, it was shipped to the Europe and combined with the European modules and departed. So after it reached to the Mercury orbit, they are separated, and by using a separate orbit, they start the observation of Mercury. So it's very nice. I'm looking forward to these observations. Okay, so I will bring the this brings the end of my presentation. So I finished the electric propulsion term, and the next time is the micro-propulsion 2 weeks later. So thank you very much. ありがとうございました。And any question?
Thank you, Professor. So yeah, if anyone has any questions, I think there's one in the chat, which I can read if you want me to. So it says, thank you, Professor Koizumi, for the presentation. With power becoming sparse farther away from the sun, is electric propulsion still a good propulsion option for missions towards the outer solar system, Jupiter and beyond?
Yeah, good point. Yeah, so I say by using electrical solar power generation, it might be Jupiter to be the farthest limit. Further than Jupiter, electric propulsion is not so, solar electric propulsion is not so good candidate, I think. And for that, we need chemical propulsion that we had done in Voyager or spacecraft, or as a future technique, nuclear power generation are required. So sometimes we call it as nuclear electric propulsion, NEP, and it would be the best candidate for outer solar system, I think. But as I explained as a first class of this course, usage of nuclear power is very difficult. Technically also very difficult, but in other reasons, politically somehow difficult. So we have to overcome these problems.
Sure, there's a second question. On the context of the Dawn mission, do all these on and off cycles represent additional operational challenges?
So your question is about why Dawn conducted the on-off cycle? Or,
I think it's more if the number. So if the number is an issue from an operational standpoint, so turning on and off, you know,
I think it becomes one of the challenge. But usually we have to operate like this. I mean, so I say that this is a standard operation. One reason to stop the ion thruster during the journey is to measure the spacecraft position. So space exploration, measurement of the spacecraft position is very important, especially to conduct gravity assist. And sometimes we stop the thruster to measure the position. I mean, so spacecraft position was measured by using the communication waves, Doppler shift, and time delay from the time delay of the communication wave. But if there is acceleration to the spacecraft, that measurement accuracy is decreased. So for better measurement, for better accuracy, we need to stop ion thruster. So this is one reason to stop the ion thruster. Also, another typical reason is to change the attitude. So some spacecraft has a very big antenna to communicate with Earth. And such kind of big antenna has very high directionality. And this means we need a very accurate alignment. We need very accurate alignment. And for that, we have to change the spacecraft attitude. And sometimes that kind of attitude requirement and thrusting requirement is, opposite. So when we change the spacecraft attitude, we have to stop the thruster. So this is another reason. So what I want to say is that typically we have to conduct this kind of on-off operations. But I think this on-off is not 10-second on-off or 100-second on-off. This is a weekly on-off like this, I think. So 1 week operation and 3 days stop, or 2 weeks operation and 1 week stop like this. But from the lifetime, too much, too high on-off is actually not so good. Yeah, it's right.
Great. Maybe we have time for just one more question, which is in the chat. What are the potential malfunctions related to this kind of propulsion?
This is also a very good question, and a lot of possibilities. Actually many. So many one. One is a grid system. As I said, the grid system has a very accurate alignment. So the distance is just 1 millimeter, like that, something like that. And if some kind of metal flake is put in this grid system, and if it shorts the grid system, ion thruster does not work, and it's one of the malfunction potential. And inside plasma generator, high energy ion sometimes erode inside the materials, and those eroded materials has potential to go to the grid systems, and one potential. And also another malfunction mode is power source. So we need to use high voltage power source, and especially if you have a switch on power supplies, sometimes the switch can become a malfunction. So if you have a mechanical switch, and such kind of switch has a possibility of malfunction, and I have had such kind of example. Also, electron emitter is very critical, essential device for ion thruster. And in the case of Hayabusa 1 spacecraft, some electron emitters, its performance were decreased, and it becomes a trouble source. Yeah, so we need a lot of tests on the ground for ion thruster. So these are very new propulsion technology. Yeah.
Okay, I think that was great. So I think we can wrap it up here. Thank you everyone for joining, and thank you for the questions. I would like to see you all in what is it, 2 weeks for the last part of these seminars. And with that, thank you, Professor, and have a good night.
Yeah, thank you for coming.
Bye bye, everyone.
Yeah, see you next 2 weeks later.